Well, very good. Well, it's my pleasure. I'm Dr. Robin Murphy. I'm Director of the Center for Emergency Informatics, and this is the latest episode of Disasters and Donuts and Disaster Seminar Series. And we are so fortunate to have Dr. Legion in here today to talk to us about his work in sensing frameworks for threat detection in metropolitan areas. He comes from a strong wireless background. The Rutgers is famous for its WinLab, for its working wireless, and then working with Bell Labs in New Jersey before coming to Prairie View in 2003. I met you at the IEEE Technologies for Homeland Security Conference. I was very
Okay, I know you
impressed with
from
your
Hong Kong.
work in that. So we've seen each other in each other's work, but it's really reminded that we need to bridge that gap between what the whole 24, 34 miles between our campuses. So let's welcome our speaker today.
Well, thank you very much for Dr. Murphy's invitation, and I'm glad to be here. So today I'm going to talk about a project that's lasting for the last 2 years, mainly. So it's about actually radiation detection using sensor networks. And this is joint work with my colleague, Dr. Fuller, from my same department in Fairview. He's more of taking care of the devices for radiation detection. So I'm taking care of the signal processing and networking side of the project. So that's how the collaboration is. And Dr. Simpson from Los Alamos. So they basically give us more input and guidance on what kind of nuclear detection device should use, and because it's related to nuclear non-proliferation kind of effort. So that's why his role in this project, and it was supported by DOE. So this is the outline of my talk. So I'll first give a kind of motivation why we do it and what kind of background, and then the framework that we propose. Actually, the concept is done by many other people, but in this specific context, we have to tune it towards something that more fits in our objective. And then I will highlight the hardware-software platform we've been using, and then focus on two things. One is the corruptive detection method. Basically, we propose a kind of a new mathematical tool how to do the detection, and then some preliminary results, and then I will give some conclude remarks and open problems, and also some photos from the lab. Okay, so what are the background of this work? So, for instance, we all heard about the Boston Marathon bombing. So this is actually a map I take from Wiki about how it happened and where is the location. So you can see the bomb explode at 2.12 here. It actually happens at the end of the marathon. And if you look at the map, one thing is for sure. There are so many streets, crossing roads in this area. So a lot of the security measures taking place, for instance, at the seaport or airport, where you have a choking point. When you go to terminal, there's only one way you can get in. And there they have these big detectors. You have to do this, right? And although you don't want to, but you have to do it. And all your luggages, everything goes through the scanner, right? So in those kind of situations, it's relatively, I wouldn't say easy, but relatively doable to scan everything and get it controlled because you have a single choking point that allow you to do that. However, in this case, for instance, it's impossible. I can't, shut down all these streets. Maybe there are hundreds of them, and I can't prevent people from coming in through different entrances. For instance, there may be somebody could go through a building and then use the door of the building to get on this street. So there's no way I can set up detectors in all these different places and scan everybody. That's almost impossible, right? Think about another scenario where I take this graph from the Memorial City Mall. That's just in Houston. So this is a map of the mall. So you can see, for instance, there are a lot of shootings and things happening in malls. So why not we set up choking points and check? turns out it's also almost impossible. Even in this mall, which is not very big, there are 7 entrances, formal entrances, okay, which means big, doors. But there are also, if you see here, are restaurants surrounding, and all those restaurants have back doors you can get into the mall. So which means if you want to scan everybody, you have to set up maybe 20 choking points to scan everybody, which is almost not possible. And people are getting nervous when you do that. So my point is this: in a lot of these situations, it's not possible for us to set up a single checking point to check everybody. So also you have to monitor all these different places, which makes this very difficult if you want to detect any kind of specifically nuclear, chemical, biological agents, this kind of thing. Because so far, fortunately, is that in these events, there are no dirty bombs or this kind of situation. It's still just a bomb. If it's a dirty bomb, the situation will become much worse. So the idea is that in the NSA, their view is that can you design a system that may work in this type of scenario, rather than at a seaport or at the airport, you can easily control the flow of traffic. And then, for instance, at seaport, all the trucks have to go through a specific inspection station, and they control your speed, they control your location, they use this huge detector to detect what's inside your your container, this kind of thing. So that's the background. So we see that in this kind of situation, the traditional limited fixed number of sensors, fixed locations may not be sufficient for these situations. And there are also issues like if you use distributed sensors, typically those sensors are small, okay, have limited capability in terms of sensitivity and computational capability. So the concern is that the required information and computation could be high. That's one thing. Second is that the response time, because for all those situations, especially try to detect a dirty bomb or that kind of thing, time is critical. You can't say that, okay, give me the information, I will spend an hour to compute what's happening and then tell you what to do. So that's almost useless, right? So we expect something like threat detection as well as response. For instance, indeed, God forbid that there is a dirty bomb exploded. You send in response team. They also need sensors with them to tell them exactly what's the radiation level at each different place at exactly what time, so that the response team will know, can I send a person, say a medical person or firefighter or National Guard, whatever, do they need protected from radiation? What level of radiation we're talking about? Things like that, right? So we believe that we do need to set up frameworks for this type of task. Now, one project caught our eye. There are a lot of similar projects I have to mention. This one specifically, my student found it about 2 years ago, I think, 2012. That UC San Diego has a project. It's for a totally different context or application. But it's interesting to us, which is UCSD developed their own air quality sensor, which is wearable. So you see this box. That's this sensor they package, and then you can mount on your backpack. So the idea is that they want to monitor the air quality in San Diego in real time, like at which location, what's the air quality reading, at what time, at what location. So that's the product. So that's the app they developed. So by looking at this product, it gives us an idea of what we call community sensing. The idea is that, okay, instead of put a few high-end, large detectors at certain choking points, like in airports or seaports, for this specific type of application, it may be possible for us to deploy relatively cheap and small-scale sensors with community members, and then collect information from community members, and then get real-time reading from different locations at the same time. and then the community member can benefit from this reading. Okay. So this is possible by recent advances in sensor technology, as well as the proliferation of smartphones. Because these days, almost everybody has one. So, shut it down. I mean the volume, because sometimes somebody calls me and it's disturbs. So
you ensure that you get the appropriate data for detecting
I will talk about it. Make it mute first. Okay. So we see that the UC San Diego City Sense project, their project is very different from what we need in the sense that it's a delay tolerant application. For instance, if you know the air quality 10 minutes later, it's not damaging, right? So it's not going to kill somebody or something, right? But for our threat detection, you need timely reporting. In other words, I can't wait 10 minutes. The other is that in their product, if you look at the design goal, their goal actually focus on power saving. In other words, their device, because they want it to last longer without charging and all that, concern like a smartphone. So their sensor was optimized not for performance per se, but for power saving. Okay, but for us, again, we need really accuracy as well as quickest detection. Okay? So here is just a schematic that my student draw. So for instance, you have this open area, so you have different corridors or streets. So a suspect with a dirty bomb can walk along the streets, and you have these different community members with their own detectors to cover different ranges, and they can either access a central controller through, say, a Wi-Fi or 3G data or any type of wireless communications, or they can actually, if it's a police officer, he can use P25, the police radio, directly communicate with each other, exchange data. Okay, so hopefully by this kind of setup, we can monitor an open area with a lot of the community members involved. So that's the basic concept. Now, in terms of hardware and software involved, for our specific project, this is the device suggested by the national lab. So it's a scintillation-based nuclear radiation detector. So it basically counts, I believe, the gamma ray. I'm not a nuclear engineering person, so I can only repeat what they told me. So it seems when nuclear radiation happens, the gamma ray basically heat this crystal, some kind of device in this scintillation tube. It's a tube. So when it's heat, it triggers an electric charge. So your so-called multi-channel analyzer will receive a count. So basically, you kind of, it's almost like a Geiger counter kind of stuff, but it's more sensitive or something like that. So basically, this piece of device will give you the count of radiation. And then we paired it with a Bluetooth transceiver. So I think the newer version of Bluetooth can be a little bit more energy efficient. 4.0 version 4.0. And then this Bluetooth will connect with the smartphone using the Bluetooth communication. Because usually you can put your smartphone in the pocket and then hand the detector on your belt or on your backpack, things like that. The size of the detector is not this. So this we call the community member equipment. So basically, I think the smartphone, everybody has it these days, so it's not an issue. But this piece of the device has to be provided to the community member. But typically, it's police or some emergency response person or employee of a certain organization. And then the information may be uploaded through different wireless technology. It could be Wi-Fi, it could be cellular system provide high-speed wireless data, like Verizon, AT&T, all these provide these services. And also, I didn't mention here in this graph at least is that the smartphone between community members may set up direct ad hoc communication using either short-range wireless technologies or using some specific band. For instance, police can use their 700 megahertz band to communicate directly. So you could either have a centralized information fusion or distributed one. So it's by choice. Now I want to fast review some background information about radiation detection. A lot of the work actually done by the national lab, including the collaborator his group also have done some work here. So in general, the detection of radioactive sources have been done for large single detectors long time ago. So if you read this book by now, it has summarized a lot of the results. So it's well studied. Now, in recent years, starting in about early 2000 up to the most recent work, this is done at UC Berkeley, sponsored by Department of Homeland Security in 2011, is that people think about similar things. Can we set up a sensor network to monitor a large area rather than a choking point? So there are a bunch of work, but none of them consider kind of this specific smartphone paired sensor type of work. And none of them actually consider how to optimize the detection by doing distributed kind of decision making. They are mostly centralized. All right. So in terms of two things that I want to talk about specifically about detection is that when we talk about sensor network, naturally there are something we can take advantage of. One is the spatial correlation. When you have sensors nearby each other, the chances are the measurement is correlated. And indeed, in earlier work, actually in 2007, from National Lab, they show that very simple case. If you put three or five sensors along a straight line, and they ask a vehicle with radioactive sources to pass by these sensors in a straight line, they show that if you do so-called coherent addition, the reason is that there are delays because speed. Again, the detector has certain angles of exposure. That means that the radiation source only appears in your angle for a certain amount of time. So you have to, when you add the measurement, you can't just blindly add them. You have to adjust them so that their measurement corresponds to exactly the thing happen at the same time instant. So that's what they call it, coherent addition. It's kind of a very straightforward way of taking advantage of spatial correlation. So today I'm going to propose, I would say, a little bit more formal or more powerful tool. I think a lot of your computer scientists know, which is the delay propagation using message parsing. Of course, it needs certain kind of collaboration between different sensors. Now, the other thing I want to point out is that quickest detection actually is a very powerful tool. It's been developed a long time ago. So if you look at the earlier literature, it happened in the 1960s. If you read Page's paper. So it's an old technique. However, there are many recent work on this. For instance, Professor Vervalli's group in Champaign. So they did a lot of work in the past 10, 15 years using the technique in sensor network context. And it turns out that there are a lot of methods to allow this quick detection technique to be used in practice rather than just theory. So that's something interesting. Again, the challenges we face here is that there are a lot of uncontrollable factors. For instance, all the backgrounds, like the wall, the building, people, we all have radiation. So basically, if you use a nuclear detector to detect, the reading is not zero, even there's nothing here. Okay, so there are background radiations, although very low. The reading may be very low, but we do have background radiation. So, and it's fluctuating too. So according to our measurement, sometimes you got say 83 heat per second, sometimes you got 72. It fluctuates. So the problem is that for any detection problem is that when it fluctuates, how do you distinguish from a real event from the noise? So that's always an issue. So let's see. How do we deal with this issue? So first of all, we conclude that a single detector probably is not a good idea because it cannot achieve very good performance. This has been, again, repeatedly proved in existing literatures. And also coverage area is an issue. So we do need cooperative sensing from all the members of this community. And in this specific work, we actually consider two techniques to help us. The belief propagation helps us take advantage of spatial correlation between sensors, and the quickest detection exploits the temporal correlations because we are considering mostly a moving target rather than a stationary one. So since it has a certain specific trajectory, we expect that there will be temporal correlation together with spatial correlation. So we what we did exactly is that we kind of take a very popular quickest detection technique for the cumulative sum test, and then incorporate BP in that framework. So basically, we use belief propagation to do a snapshot, kind of, in one time interval, and then along the timeline, we apply the cumulative sum test. So that's the highlight of the structure of the detector that we designed. Okay, so here are some mathematics. The modeling. So we follow basically the standard setup. So the detection problem can be formulated as a standard hypothesis testing problem. So you have two hypotheses, H0 and H1. H0 basically says you receive, so your sensor receives the heat, right? The heat is basically implies the radiation intensity. So when again, your detector has certain sensitivity. That means it only covers a certain range. So outside that range, pretty much, you probably don't receive the heat. So because of that, we define an x-edge, which means that's the average radiation at the border of your sensitivity range. So that means if a radiation source is at the border of the radiation detector's range, what would be the level of intensity you will get at that sensor? Okay. So of course, if this is less than that value, we declare that there is no radiation source. Otherwise, there is one. Okay. So that's the hypothesis we set up. And as many literature suggests, for belief propagation to work, you need a model. Okay. And the most popular, and we believe to be reasonably close, well, the behavior is reasonably close to reality, is the Markov random field model, which assumes that if we have neighbors, right, the non-adjacent neighbors, like me and somebody not directly neighbor to me, the measurements are independent. Okay. But the different measurements are pairwise Markov. So that's basically the Markov random field model. And we assume a couple of variables. The observation, which we denote by yi, these are the noisy measurement you get at the sensor. We assume it's follow Gaussian distribution. And the mean value of that, which is xi, which is we believe is the true value, because what you measure is noisy, right? But there is a true value. The true value is xi. But it's also a random variable. It's not a constant. So we assume the priori distribution of this xi is also a Gaussian distribution with certain mean and variance. Okay? And we also assume for instance, the distributed detection scenario, the sensors will have short-range communication capability so that they can talk to each other within their transmission range. So this is the.
I have a quick question
Yes.
about that. So there's the transmission range, which is the communication range, and there's the range of statistical dependence, which is in the MRF. Are these two ranges the same? So a neighborhood in the MRF equals a neighborhood.
Yeah, that's a very good question. Actually, we assume the transmission range is larger than that. That's a very good question, because later on, actually, we see that this different ratio of the range actually play a big role.
Okay.
Okay. Anyway, I guess a lot of you already know this, so I will not go into too much detail. So basically, the idea of belief propagation is to calculate the condition, the marginals, based on local information as well as the message passed from neighbors. So basically, we write this additional probability in terms of local information as well as the message passing from neighbors. So these are standard techniques. So if you look at any machine learning book, it's right there. Now, for our specific assumption, under our specific Gaussian distribution assumption, we can easily derive the PDF, conditional PDF, in this format. Only Gaussian allow this to be mathematically trackable, kind of easy to track what's going on. And then this is how A and B related to the mean and variance of the measurements, and one is the measurements and the other one is the mean value. Okay. So the message parsed from neighbors I to J would be in this format. Again, I'm not going to go to the details. It's not so difficult to derive. This is kind of a standard technique. But for a Gaussian assumption, you can derive this. And after derive this, we can follow the message parsing procedure. Again, this is kind of quite standard that, you have measurements, you have, again, Z, I haven't mentioned Z. Z is actually kind of your decision, whether there is one or there is no source, so radiation source. So the input would be the noisy measurements. So if you follow this procedure and exchange information with the neighbors, this is how belief propagation takes advantage of spatial correlation of different measurements from different neighboring sensors. And so one thing, of course, we know that here's the tricky part, which is in belief propagation, we all know that whatever the message parsed from I to J cannot be passed back. The reason is that you don't want to artificially amplify a belief. Like I believe in something, I tell you, and you come back and tell me. So it's kind of, you learn that partially from me. You shouldn't come back and tell me that part to artificially amplify my belief. So that's basically what belief propagation always, you have to take care of that. But the issue is this: if you don't consider time is the snapshot kind of thing, it's fine. However, you see, if you keep doing that, what happens is this: if you consider a timeline, now whatever I tells J, because it doesn't pass back, but that information may be from before. So in that sense, BP doesn't consider timeline, create a problem of you lost temporal correlation during the process. So in that sense, DP is not so DP is not directly applicable if you want to incorporate temporal correlation. Let me put it that way. So that's what we think. We should need something that helps us take care of the temporal correlation, because remember, we're talking about a moving target, and the temporal correlation is strong. Like, you know, it can vanish from one range of a sensor and appear in the neighboring range of sensors. So the technique we choose to take care of it is the quickest detection. And quickest detection is, like I said, it's a well-established technique. And the format is like this. So the measurement, say it's S, and then T star is the time instant that something happens. Okay? Emerges, a radiation source emerges, something happens. Then the basic idea or assumption is that the measurements follows a certain distribution when that event doesn't happen. And when suddenly some events happen, then the distribution changes to a different one. Okay, so that's the basic assumption here. Now, if you believe that's true, we can define the detection time, T of D. So basically, that means that's the time from the event happened to the time that your detector telling you something is happening. So that's TD. Okay? So the false alarm rate would be simply the probability that TD less than T star. In other words, that thing doesn't happen yet. Until T star, it will happen. Your detector already telling you something is happening. So that's a false alarm. Okay. And then the average detection delay can be formulated like this. And then the quickest detection problem is simply minimize the average detection delay, subject to some bound false alarm rate. So that's a very standard formulation. Okay. So the idea is, again, like this. So what you're observing, again, is a random process, not a fixed number. So it fluctuates. Now, what happened is that we can use the well-established log likelihood ratio. So basically, you can calculate the log likelihood ratio. Basically, that's the ratio between before change and after change. So if there's no change, this ratio will simply fluctuate around 0. Okay, so if you plot the log likelihood ratio, you know, it's just it's not a constant, but it fluctuates, sometimes positive, sometimes negative, but it will be mean at 0. Okay? However, when you have a change of distribution, what would happen is this log likelihood ratio will slowly climb up. So again, it's not uniformly like this. It still fluctuates. However, the main trend, because remember the distribution changes, right? So when you calculate the log likelihood ratio, this ratio will be positive even. That's the trend. So eventually, after a while, if you have a threshold value, when it hits the threshold, the detector will declare something happened. Okay? So you can see, of course, the threshold value plays a big role here. For instance, if you set the threshold very low, what would happen is you will have a lot of false alarm. Remember, because it's fluctuates, right? It's not constant. So it may hit your threshold to give you a false alarm. However, if you set, say, I don't want false alarm, so you set your threshold very high, what could happen is that your detection delay will be very large. Remember, again, when something happens, which is this red line here, you know, it takes a while for this to climb up. If your threshold is too high, it takes too long. So it's a natural trade-off between detection delay and false alarm rate. So you have to set your threshold kind of optimally, although there is no systematic way of knowing what is the optimal. Okay. Anyway, so we can use this kind of formula. So LK is the log log likelihood ratio, and then you take SK as the cumulative of basically sum of the log likelihood ratio, and you keep taking which one is the maximum. Okay? And then when the maximum across the threshold bound, you will declare detection, and the minimum time to achieve that is your solution. Okay? So that's why it's called quickest detection. In order to use this, like I mentioned, we can't directly use BP or QD. We have to merge them. So we modify the belief propagation. In the belief propagation, I didn't show all the mathematics because it's tedious. In belief propagation, you need to calculate. Yeah, you need to calculate this. Okay, the marginal. So when you calculate that, actually it's a bunch of product of the local information. And turns out that can be rewritten in terms of S of K. So if you do the mathematics, you will find that actually, actually I can incorporate this into the BP calculation. So that's how we integrate these two methods together. And this is the result here. Again, I don't want to go too much into the details. But basically, after we integrate them, the algorithm would look like this. So the detector, in order to take advantage of the time correlation in addition to BP, we give it a kind of a memory window so that it will kind of locally store some information up to L length. Okay? For instance, in the simulation, we set L equal 10. So that means I don't throw out my measurement for the last 10 intervals. I keep them, and I move along. And then the message parse between the detectors include these L different pairs. Okay? And then when making a decision, the detector take all the L computed beliefs into consideration and using belief propagation, using quick detection to make the final decision. Okay, so those are the theory part. So we did some testing in the lab as well as some simulations. The first things we did is actually this is a CZT detector. It's a commercial off-the-shelf we purchased from the company. And the students hook up this in the lab on a long table like this. Several of them, actually 3 or 4 of them. And then what we want is first to try quickest detection to see whether this time correlation thing will help us or not. So the experiment we did is this. Again, I mentioned that it's always the main difficulty is that how do you distinguish something new from background? So in order to make it more interesting, we put this is a cesium-137. It's one type of nuclear source. I don't know what it is. But anyway, this is what they give us. So we put this source kind of relatively far from the table so that the background radiation that this source created would be benign kind of radiation or not that strong. So we use it as a kind of uncertainty, if you say. It's kind of background disturbance. And then the real radiation source, which is again the same material, but much closer to the we actually let it move along the table. And we let it go through the entire table. And then we also try different background radiation by tuning the location of this source. Right? Let it very far away, medium, or very close. To create 3 different cases where you have strong background disturbance, one is medium, one is almost not much. So and then we try to see So we did see that affect performance a lot. So what's plotted here, the x-axis is the probability of false alarm rate, and y-axis is the detection delay. So you see the natural trade-off, which means you want low false alarm rate detection delay is large because we tune the threshold. That's how we achieve this. Okay? So these different dots on the line correspond to different threshold values that the student tried. And this different curve corresponds to different radiation, background radiation disturbance, which obviously this blue one is the strongest disturbance. The black one is medium. Actually, the other one, the weak one, I guess the student put in another room or something. So it had no effect on detection. So we got perfect detection, kind of. Anyway, you can see that, for instance, if you want 10% false alarm rate at medium radiation disturbance at the background, you need about 6.5 units of time to actually find it. Of course, for the strong radiation, you will need almost 9.5. And this is, again, the sources, which the sources that we move along the table. This one is unshielded. Unshielded means we don't put a lid in front of it, so the detector will fully receive all the hits from the source. This graph shows it's shielded, so we actually put some metal. So in this case, you will see for the same false alarm rate, the detection delay is much, much higher. It's almost 5-6 times higher than the unshielded, which is expected because we have to set the threshold much higher so that we can be sure that, because it's very hard to tell the shielded radiation from background radiation because the value are so close.
You shield the entire source?
No, we only
Just
shielded
between
one
and
side because the detector only have a certain angle of view. So if you block this, pretty much you block everything. Because when they hit the wall, I don't think they reflect much, unlike the real wave. So we really don't shield the entire thing.
Because that'll change quite a bit. We've worked with
Oh,
cesium
okay,
sources.
I see. Yeah, so I don't know much about nuclear stuff. So this is what we observe. Okay, so after we see that quickest detection can do some good, but let's see what more sophisticated scenario we can test. So afterwards, these are not based on experimental data. These are basically we generate some simulated data based on the measurement from the experiment, but it's kind of artificial. So these are not tested in a sense. So we consider two scenarios. One is that in a street, so you have an avenue, street, source kind of go around, and these red dots are the sensors that we deploy. And another one is more kind of random. So we randomly place the sensors and allow the source to go a sinusoidal waveform. So what we see is that, okay, first of all, for the first case, if we only turn on, so in the experiment, in the simulation, we have 100 sensors altogether in the entire field. And then in the first experiment, we randomly only turn on 21 of them. If that's the case, you will see that, okay, actually, for all the 21 sensors, these are the 21 sensors we turned on. The y-axis is the detection delay. And if it's 0, actually here means it doesn't detect anything. It doesn't mean detection delay is 0. It means actually they don't see anything. Okay? They don't detect anything. So you will see the only correct detection is 1 that near the way that it passed. Okay? So that's an issue because, as I mentioned, this detector that the community member has usually are low sensitivity. In other words, they're not very reliable. So if only one policeman suspects, oh, my detector runs out, well, it's not so assured, meaning that it could be just a false alarm, because we see that a single detector could have very large false alarm rate, right? So if that happens several times, next time when it's real, probably still don't know whether it's real or not, right? But if we take on and say turn on all the sensors, say let all the community members, the 101 sensors participate, what you will see is much assured detection. In other words, all the sensors along the street will have a kind of a collaborative detection. Okay? So if that happens, I think pretty much you're sure that something is wrong. So that's just one proof of concept saying, community sensing makes sense in this case. Okay. And then, so here again, these two experiment simulation, we don't use BP at all. We just use cricket detection only. Okay. Now let's see how BP may help each other. That's where your question is. The communication range here is much larger than detection. So in this case, we still just turn on 21 of them. So a lot of them, if you see originally, right, a lot of them may have some detection later, but because they're far away, so their detection is kind of very weak. So in the past, without BP, without taking the spatial correlation, they probably won't declare because they're not sure, without input from the more assured member. But you see here, what happened is that when we apply the BP into quickest detection, almost all the sensors report that there are something, even without turning on all the 100 sensors. So in some sense, we see that because in reality, probably we don't have the money or the necessity to equip everybody a sensor. So we may just give policemen some, emergency response person. So we don't expect the density of the sensor nodes to be so dense that you can always have everybody report, right? So I think that justifies why BP kind of integrate with quickest detection will help in this kind of sense. And for the sinusoidal waveform, the more random setup, we also did some simulations. So this time, what we did is that we tried BP without quickest detection to see what happens. So in this case, again, we see the natural trade-off. For instance, there are certain thresholds allow the false alarm rate to be bounded. Okay? And for the same threshold, you also have the misdetection. So you have to achieve a trade-off. For instance, if you set threshold very, very high, you have low false alarm, but then your misdetection also high. Similar trade-off that we see in detectors. However, when we apply BP with the community sum quickest detection, you will see an interesting phenomenon, which is there are certain ranges of thresholds. For instance, from 2 to 3, you will see both false alarm rate and misdetection both goes up. That's kind of very interesting because we never seen that in any kind of standard detector, because there are always a trade-off. You want higher accuracy of detection, the miss rate low, the false alarm typically will be large, and vice versa, right? But in this case, we believe because of BP and quickest detection take advantage of both correlations, somehow that give us a better performance somehow. We still explore the theoretical proof that this is indeed the case, because this is simulation. So I can't say 100% that this is correct. But that's what we observed, and we are very excited about this result because it deviates from the traditional kind of belief in detector design. Okay, so quick recap. So in this work, we are focused on detect threat in kind of open environment rather than choke point. And we propose using a kind of distributed community sensing framework. And the major theoretical contribution would be joint belief propagation quickness detection to make the detecting more effective and accurate. And we have done some preliminary work. Now, there are a lot of open questions. For instance, students currently are working on, for instance, in terms of system level, how often the communication should happen at different points. And then we want to explore some theoretical results on the density of the sensors versus sensitivity of the sensors, as well as what you mentioned, the ratio between communication range and sensitivity range, how that affects the entire system level performance. And we also want to see what if we have missed data, false data during this message exchange or the information filter, what would happen in that scenario. Okay. So there are a lot of issues, and also the experiments. The students still struggling to do more realistic experiments because they want experiments, not simulation. Okay, there are some references. So we have some Homeland Security paper talk about the work. So I will just spend maybe another 5 minutes about the group that we have at TV. So I'm joining TV in 2003, and that's part of my startup package. I started a wireless communication lab. So the research typically focus on wireless network-related research in terms of cognitive radio sensor networks, and a little bit security. One of my students is working on homomorphic encryption for some very specific thing, kind of privacy preserving type of thing. In terms of test beds, I have some equipment on USRP, USRP2. I also got some WAR platform for mainly cognitive research. And I also have some sensors in the lab. The older ones back in 2004 are from Crossbow. They no longer produce them. They get out of sensor business and go to mainly the flight stuff. And I have some recent sensors from Texas Instruments. And recently, my students are working on, smartphone paired sensors. I think we have one. Yeah. So this is the sensor my student working on. So what it does is it can measure temperature, humidity, light, air quality. So this is done by a startup company. So basically, we have an app. I can use Bluetooth to connect to it, and then use the app to control it. Then the reading will be fed into the app, and the app adds the GPS location data and the timestamp. And then I have another module in the app to transmit it to a background server, a web portal in my lab to collect the data. So here is a graph. So I have a student actually live here because his wife studied at College Station. So he drive from College Station all the way to Houston. And this is the temperature data that he uploaded along the way of driving. So this is one thing that he's interested. So I said, okay, go ahead, let's try it. Eventually, the idea is that if we have the radiation sensor, that's produced by Los Alamos. So we hope to do similar stuff. So we are going to program an app, communicate. We have to append that sensor with a Bluetooth module. They don't allow wireless in Los Alamos. They say no wireless in the lab. Inside the lab, your phone, your computer, everything you give to the security people. You go in, no wireless, period, no wireless. So we can't do our experiment there. So what they give us is just a sensor. So we have to append a Bluetooth module to that sensor and hopefully repeat what we did with this. So kind of communicate with the smartphone and then upload the data to the web portal we have. Okay, so in terms of students, I have 6 PhD and 5 master students graduating. I have supervised some senior design groups around the years. Currently in my lab, I have 7 PhD students and 2 masters. And I periodically have undergrad senior design group working in my lab. And the funding is moving from this area. Okay, thank you for your attention.
So some quick thoughts for you is that I don't know if you're familiar with gamma pits. There's a company that already sells an app that detects radiation based on the interference to your cell phone. And for the past 2 Winter and Summer Institutes, we've had them out here because we've had live radiation exercises out at Disaster City. Okay. And so that may be something you want to think about, both getting the data from the gamma pits, right, because that'd be very easy, and also thinking about running an experiment at Disaster City because nuclear engineering can put a large cesium source over one of the buildings, and you've got a whole 4-block area that would be great with people and cell phones, and that could give you some information. So keep always, we try to send out about the Summer Institute, but that's the last 2 have been on radiological. Okay. So anyway, that would be, and we also have, I think, either 5 or 10 Radiac sensors that we can learn through, part of our large MRI. Oh. And so Radiacs are the standard radiation sensors that people carry on their belts. So those things came to mind as that's great. That's why we need collaboration. Yeah. Otherwise, I don't know what you do. You don't know what I do. And I sent email to the nuclear engineering department. Any questions for a speaker?
I had one question about you made some assumptions about the measurements being Gaussian. Yes. I was wondering, does that reflect reality? I wouldn't expect them to be.
No, I don't think so. Right. Frankly, there are always gaps between theory and reality. For reality, what the distributions are, I have no idea. But what I was told is that, well, at least my students did some literature and they see, okay, in some of the reports from previous work, from especially Los Alamos because they are our collaborators, so they provided us some reports. From the reports, what they say is this: they believe that this assumption wouldn't affect the performance too much. That's what they said. For whatever reason, they didn't say. So we just take that and then say, okay, this probably is a reasonable assumption, and also it's mathematically much easier to derive the results. If it's a different distribution, how difficult it is to derive those results, I don't know. I never tried. So.
It should be, it seems like it would be very easy because a radiation source, well, it's sort of scary in other ways. It's very easy to model mathematically. Poisson or exponential.
I do believe somebody use Poisson. For instance, the work from UC Berkeley, they use Poisson.
The problem is the absorption rate. There's the different materials will absorb different. So if you're not, if they weren't sometimes the radiation source wide open, and you are blocking it wide open, so much more. Which is why I asked about where to put a shield, because that can dramatically affect. And that reminds me of a question I had, is that I wasn't sure how it was being handled over time. The temporal aspect is that it seems like the more readings, if I'm carrying around, I've got a device in my smartphone, and I get lots and lots of hits from seeing the same place, versus there's over time 4 or 5 people walk through the same place and they get hits on radiation.
Oh,
How
our
is that
sensor,
counted?
our sensor.
How is that counted in your belief model?
Well, our sensors are stationary. Our target is moving. So our sensors are not mobile.
Okay, so you're looking at the
Yeah, at
handhelds
least
with
in
the
so
cell
far,
phone.
the experiment and the simulation will always assume our sensors are actually stationary. And the target is moving. It's interesting. That's another interesting question, which is, what if the sensors are also moving? We didn't actually explore that aspect yet.
Yeah, the gamma fix people need to do it.
Yeah, I'm sure I'm going to. Can you email me? Because
Yeah,
I don't know
maybe
this
introductions.
work.
Yeah, that's we've been working with it for about a year through our
Oh, okay.
Edge Industry Consortium.
Okay. I don't know this.
Very cool.
Actually, I had a very, very similar question. So under the assumption that the sensors are stationary, I didn't quite see where there's the dependence on the velocity of the item you're tracking. It seems to me that the potentials in the belief propagation would change as a function of how quickly the item is moving. Right. So if I take a snapshot here, and then there's another snapshot 1 second later, if this device is moving slowly, if the source is moving slowly versus quickly, it seems like there would be different information you would propagate over the BP. So it seems like there's a dependence on the velocity of the.
Yeah, absolutely. Basically, we kind of at least during the simulation, the speed as well as the interval, because remember, BP is only running in each interval.
Yeah.
The quickest detection take off the long range, right? So the interval that allows the BP to run has to somehow correlate with the speed. So I guess in that sense, we cheat a little bit to assume that we kind of know what is the speed of, like a pedestrian. If you're not running very fast, what is your speed range, things like that.
But is the single iteration of the belief propagation, single interval in the belief propagation, is the assumption that maybe the source will move one network distance, or one neighborhood distance in one unit? Okay.
Something like that. Yeah.
I see.
Any other questions? Well, if not, let's thank our speaker. Thank you so much. And it looks like we lost Alex Frenson.